Hey everybody, welcome to lesson 6 in unit 1 for pre-calculus. Today we're talking about transformations of functions. Up here at the top of the notes you can see the standard form for equations of a function. I'm going to highlight that for you right here. So we always want to be able to go back to that standard form to write our parent functions. Now, in geometry and algebra 1, you've probably looked at the 4 different types of transformations in detail. Those would be dilations, reflections, rotations, and translations. Dilation, reflection, a rotation, and a translation. In pre-calc, we'll mostly look at reflections and translations. A rigid transformation keeps the original shape of the graph, but a non-rigid transformation is going to distort the graph by either stretching it or shrinking it. So on your notes, we have f of x plus c. That's a shift up c units, and what you would do to your values would be you would add c to the y values. And then f of x minus c, you would subtract c from your y value. With f of x minus c in my argument, x minus c is the argument, that's going to shift the graph to the right. So you would add c to the x values to get the graph to translate to the right. And to get it to go to the left, you would subtract c from your x coordinates of an ordered pair. When you want to take the absolute value of a y, you're going to reflect that negative y value across the x-axis. So the behavior, what you would want to do mathematically if you had a table of values, is you would take the absolute value of any y coordinate, where negative or the opposite of f of x, you're going to keep the x and do the opposite of the y. And when the negative is on the argument, we're going to do the opposite of the x and keep the y. And those are going to cause reflections across the x-axis or across the y-axis. Now, non-rigid transformations, they're the ones that will distort the graph in some way. So when you have a factor in front of the function, that's going to be a vertical stretch, and the factor is c. So you would multiply your y value by the factor, and it would shrink, vertically shrink, if the c value was less than or equal to 1. Let's see, on your notes, we have a little different where we have c is, let's see, we need to add to this. We have a vertical stretch. Give me a second here. Okay, I was missing those amounts. Now, if the factor is on the inside of the argument and the c number is greater than 1, that's going to horizontally shrink your graph by a factor of 1 over c. So what you want to do is you want to divide your x values by that factor. And if your factor is a fraction, it's going to horizontally stretch your graph. So you're dividing that factor by your x coordinates to get a set of ordered pairs. Okay, let's look at a few of these. We want to use the parent graph. In this case, our parent graph would be the parabola x squared. We've got a shift to the right. It's -2, so we're going to move that graph to the right 2 units and up 4 units. And the negative out in the front, that's our A value. That A value is going to cause the graph to reflect across the x-axis. So reflect across x. And in this case, we have 2, 4 as our vertex with an upside down parabola. And I had said earlier that the parabola, if the A value is a 1, the pattern goes 1 down, 1 left and right, 3 down, 1 left and right, and then 5 down, 1 left and right. So you can really quickly graph that parabola. On letter B, we've got an absolute value as our parent function, and +3 moves our graph to the left. So we have a shift left 3 units. And then -5 would move the graph down 5 units. The A value is 2, so that's a stretch factor. And that stretch factor kind of acts like a slope with the absolute value. So if we come over here to -3, -5, and the slope has a rise 2, run 1, rise 2, run 1, 2 up and 1 in both directions. It's a really easy, quick way to graph absolute value. Okay, there's 2 more. If you'd like to turn the video off and try those by yourself, you can come back and check with me. On this one, we're going to shift to the right 2 since the 2 is a positive value inside of our argument. It's underneath the vinculum here. The vinculum is like a grouping symbol, just like parentheses, and that's a positive 2. So we're shifting the graph 2 units to the right. Then -3 means we're going to move that square root graph down 3. Oh, that's a funky looking 3. Make that look a little better. And then the negative on the x means that we're going to change the x, so we'll reflect across the y-axis. We're going to reflect about the y-axis. So HK is our starting point or vertex type of point to -3, and 1 up, so it's like a sideways parabola. 1 up, 1 left, 1 up and 3 left, and 1 up and 5 left would be off the graph. And the square root parent function has been translated to look like that. Then the last one in our example, we've got -3, so that's a movement to the right 3. And then +2 is up 2 units. And the 1/2 is a vertical shrink. So we have a vertical shrink factor, but it's also a negative, which is going to reflect it. And the reflection is going to be about the x-axis. So reflect about the x-axis. And it's a cubic that's got an HK value of 3, 2. And if you just really quickly substitute a 1 in there and do the math, I believe you get 6. And if we substitute a 5 minus 3, that's 2. We're going to get a -2, if I did that arithmetic correctly. So the graph is going to start high and curve around here and then go low. That's not the greatest cubic. Whoop, I missed the cube on my equation. Give me a second to fix that because I believe it's cubed on your paper. There we go. So you had a cube right there. All right, in our next example, we're going to look at those stretches and shrinks doing three different things. We have our parent function is x squared, so I'm going to put that one in red. Our parent goes up 1, and then 1, 2, 3, and then 1, 2, 3, 4, 5, and then 7 would be at 16. So 1, 2, 3, 4 is 16, 3 is 9, 2 is 4, and 1 is 1. So this is our parent function, y equals x squared. The next one is f of 2x. So our argument is increased by a factor of 2. And what we said at the beginning was that was going to be to divide. So let's do this one in, let's say blue. So the f of 2x is a horizontal stretch, and our factor is 1 over c, so we're going to divide the x value by 2. And if you put 2x into the parent function, then the f of 2x is 4x squared. And that would be a really skinny graph, so still at the origin. But when you put a 1 in here, our y value is 4. And if you put a 2 in there, our y value is 16. So it's a really skinny graph. The blue graph, oh, I can't draw with this tablet. This is a horizontal stretch. And then in green, we'll do the other one, the half x. So the h of x is 1/2 x. So h of x is 1/2 of x squared. So that's a horizontal shrink factor. Simplifying, you have 1/4 x squared for h of x. I'm going to call this one g of x, and this one I'm calling h of x. So in this case, we want to multiply that factor of 2 times each x value to find other ordered pairs. So in this case, it would still be at the origin, but let's say we put a 4 in here. So you've got 2 would be a 1. So you got a wide graph there, sort of like that. So I'm calling my parent graph, the red graph, this is f of x. And then the 2x graph, we're going to call him g of x. And then the horizontal shrink, that's going to be our h of x graph. So you can see the behavior in 3 different colors of how those translations work with the factors inside the argument, one a fraction and one a whole number. In this next example, we're going to look at a table using some tables to go by. The graph of f of x can be drawn by connecting the points in the table with straight line segments. So you can spend a second and graph -4, -2, -2, +3, -1, 0, 1, 4, and 4, 2. So we've got our basic graph to start with, looking like this. And then we want to go visit, we'll have to come back to this in a second. We're going to go visit that. So the graph of h of x has been moved 3 units to the right. 2 units up. Oh, your paper has a 4 there. Let me fix that. There, that looks better, more like your handout. So we're going to move this graph 3 units to the right, 4 units up. We have a stretch factor of 2. So that would be, let's see, I need a place to write here. Get us a little rule about what we're going to do with the table. So if we're going 3 units to the right, we need to add 3 to the x value. We've got a factor of 2 here. Yours has -2, so I need to fix that. And we're moving up 4 on the y-axis. So down here in our table, I want to take my x value and add 3 to that to get a new x coordinate on a new graph that we're going to call h of x. We're finding new ordered pairs for this. And for the y coordinate, which is -2, we want to multiply that y coordinate times -2 and add 4. So one ordered pair would be -1, 8. So I can go back to my graph. And h of x, we could do that in a red, would be -1, +8. And then we can complete that table doing the same thing with the other 4 points. So -2 plus 3 gives us an x coordinate of 1, -1 plus 3, and then +1 plus 3, and 4 plus 3. Then our y coordinates, we're going to do the same thing, -2 times the y coordinate plus 4. So we have another ordered pair, 1, -2. And repeating that here, 2 times 0 plus 4. So we have an ordered pair of 2, 4. And then 2 times 4 plus 4. Whoops, I mean -2 times 4. Gives us 4, -4. And lastly, -2 times 2 again, plus 4 is 0. So 7, 0. So this column here, we're going to go back to the graph and graph those coordinates overlapping our original function. So 1 was 1, -2. So from here, we went to here. That's not a very straight line. Let's try that again. Oh yeah, that's not much better. And then the next one was 2, 4. 2, 4. And then after that, 4, -4. And finally 7, 0. So I'm a little challenged to draw with my tablet and draw a straight line. I have to apologize for that. Okay, so the blue graph was our f of x graph, and the red, somewhat straight lines, is our h of x graph based off of the table and the transformation that happened from our function. Make sure you have a -2 there on your handout. Okay, in example 4, we want to compare and contrast what the reflections do, because as you move through calc, you want to be able to look at a function and recognize from the family of functions what it looks like. There's our graph f of x. And we want to think about, what does g of x do? When you have a negative out in front, what happens to that? And what does the +2 outside of the argument do? So we know that it's going to move up 2 units, and the negative on the a value would reflect over the x-axis. Will reflect about the x-axis. So in red, we're going to move the graph up 2, And this graph that's going this way is now going to go down this way. So g of x goes that, upside down. And the domain for g of x would be from 0 inclusive to infinity. Okay, on B and C, we're going to do the same thing. So you can try it on your own and come back, or stay here with me. So I'm graphing the parent function f of x. Oh, I need to do that one in red. F of x is in red. And negative x is going to reflect over the x over the y-axis because the argument is on the x. It'll change the y's. I'm sorry, it's going to reflect about the y because we're changing the x's. So that would be the same graph, just reflected over the y-axis. Instead of having positive x's, now we have negative x's, and the domain is from negative infinity to 0 inclusively. And then our last one, again, a square root function in red. The parent is here, off to the right. This is our f of x. And k of x is going to reflect over the x-axis and shift left 2 units. So we say left 2 and reflect over x. Reflect about the x-axis because we're changing the y's. So left 2, and instead of going this way, it's going to go downward in the same shape. You see how that's a rigid transformation? It didn't stretch it or shrink it at all. But the domain begins at -2 inclusively and goes to infinity. Okay. Now, similar to the third example, this one is pretty lengthy. We've got a function that contains the points -3, -3, -2, -2, -1, 0, 1, 1, 1, 2, 3, and 3, 0. Whoop, 0. And we're going to use that table of values and translate the graphs. This one we're going to take only positive x's, right? So if I use, let me put two of them together so we can view both screens together. And I could make this table. So I've got x and g of the absolute value of x. So in this case, if x is -3 and I put a -3 in the absolute value, my y value needs to be +3, and on the table that's 0. You follow that? The g of the absolute value of -3 is the g of +3, and the g of +3 is 0. Okay, so let's complete the table, and then we'll graph the graph. So at -2, we want the positive value, that would be 3. At -1, we want the positive value at 1, that would be 1. At 0 is 1, and 1 is 1, and 2 is 3, and 3 is 0. So this would be our new table for those values. So what we're doing is we're taking the absolute value of x and keeping the y. This is our rule. So that graph is going to look like, let's see if I can draw this a little bit better this time. Okay, so it's going to go up and down and across and up and down. Looks like Batman ears, doesn't it? Okay, now I'm going to turn that off. You've got your table. And we'll look at the graph a little bit bigger. So this case, the rule is going to ask us to keep the x and do the absolute value of y, because the absolute value is on the outside of our function. So our new ordered pairs are going to look like that, which would make -3, 3, -2, 2, -1, +1, 0, 1, 1, 1, 2, 3, and 3, 0. So all of my y values are positive. -3, 3, -2, 2, -1, 1, 0, 1, 1, 1, 2, 3, and 3, 0. And we're going to connect those with straight line segments for our transformation. I would highly recommend that you turn off the video and try the last 4 for yourself, and then come back to check with me. Okay, here's what we have for letter C. So the rule was to do the opposite of x, and that's going to reflect the original function across the y-axis. If you go back to the original and look at it, you can see that it looks just like this, only flipped over. Where's our original? Here's the original right here. And on letter C, this piece is over here, and all of this piece is over there. Let's go look. See, just flipped over x. On letter D, we had 1/2 here, so that's going to make a horizontal stretch. You can see it's very elongated, so we're going to double the x values, and that made my table have this set of ordered pairs. And graphing that out with a somewhat straight line on my tablet, I have that. On letter E, the argument is 2x, so we're going to divide the x's by 2. So x divided by 2 in each case is going to really shrink up the graph on the horizontal scale. So it's the same shape as the original, it's just really smushed in tightly here on the horizontal shrink. And then the last one, letter F, we have a shift to the right. So we're adding 1 to every x coordinate, and I made my table look like that by adding 1 to each of the x coordinates in the original table. So it looks like the same general shape. Instead of starting out over here at -3, -3, it started at -2, -3, and we graphed the graph. So that's the end of this lesson, and I'll see you next time. Good luck on your homework.